the other side. So today I would like to talk with you about a work in progress of Giacomo and me about small-ish quantum tunnel codes. So my plan is to first tell you a bit why we thought that that was a relevant problem to look at. Then I will go into the quantum tunnel codes construction, show you that a couple of examples of codes I'm sure everyone knows in this room are actually quantum tunnel codes. And in the end, I will give some ideas on constraints that can help us to find new finite instances of such codes. So as probably everyone in this room, main goal maybe is to run quantum computation. And what you would like to do is to do that in a fault-tolerant way. So in a way so that your computation runs successfully and in the most efficient way possible. So to say with constant overhead. Here by overhead, I mean the amount of total physical qubits that your computation is going to need in order to run in a fault-tolerant way, compared to the number of qubits that the Bayer logical circuit will need. And what we know is that the threshold theorem tells us that provided that we respect these three constraints, then we can do this with constant overhead only. And what these three requirements tell us is, the first one is you need a family of LDPC codes. So LDPC stands for low density parity check, and basically means that the coding circuit of your code is low depth, or put in another way, that each qubit is only involved in a small number of stabilizers, and each stabilizer only uses a small number of qubits. Then we want this family to have a constant rate, where the rate of a code is defined as the ratio of the number of physical qubits n of the code and the dimension. The other way around, but it's OK. And third, that we need is an efficient decoding algorithm and a threshold. And all good so far. And in fact, since 2009, we had the first class of LDPC codes that actually satisfy the assumption of the threshold theorem. And those were the hypergraph product codes that have dimension that scales linearly with n, the number of physical qubits, and the distance that scales as a square root of n. So this is good enough to satisfy the threshold theorem, and in fact is better than the scaling that we have for the planar code, whose dimension is always 1, which means that you can make your planar code as big as you want, but it will always encode just one logical qubit. And the planar code is actually an hypergraph product code, but uses a seed code that is not good enough. And so we find this dimension scaling. And this is good enough for the threshold theorem, but it's not the best we could hope for. Because in classical coding theory, we know since a long time, the 70s, that there are family of LDPC codes that have both the distance and the dimension that scales linearly with n. So there is still a gap, or there was still a gap in between the hypergraph product codes that, yes, satisfy the threshold theorem assumption, and the best we could hope for in classical land. In 2021, we had the first proposal of good codes, LDPC. So good codes means codes that have n, k, and d that all scales the same. So k and d are linear in n. And yeah, we had to wait till 21 to find such instances. So what I will focus about is a proposal by Levrier and Zemmour, which are the quantum tunnel codes. And this is great that finally we have been able to find such good code family. However, no. However, the key word here is that all these family are good in the asymptotic regime. And, you know, quantum computers are not ready for the asymptotic regime yet. So just not to take responsibility, I just copy and paste this table from Wikipedia. They say that it's updated in January 2025, but I don't want to go into the merit of this. It's just the list of quantum processor based on gate architecture, and this order top-down by number of qubits, which is not, of course, the only parameter we care about when judging a quantum processor, but just to give you an idea, as I'm sure everyone knows, we have the first couple that are in the order of thousands, and all the others are like hundreds of physical qubits. So even if the quantum tunnel codes give us an example of good code families that have the best possible scaling in the asymptotic regime, we are not there yet. So for this reason, we thought that maybe looking at family of codes that were at a better scaling than the hypergraph product codes, but requires us small-ish order of hundreds of qubits was a problem people could have been interested in. So before going into the quantum tunnel codes construction, let's start from the beginning, which is the classical tunnel codes. This is what the quantum tunnel codes build on. And the main ingredients for to build a classical tunnel code, or a tunnel code in general, are a graph and a seed code, classical code. So we need to build a regular graph where vertices have all the same degree. The degree of a vertex is the number of edges that are incident to it. And to do so, we are going to use a group to define this graph. So in this example, I'm going to take the group of integers mod 4, and I'm going to take a set of elements in this group. So here is A, 1, 2, 3, and I'm going to draw a vertex for each element of the group. So I'm going to have 4 vertices here, and then for each vertex, I'm going to do an edge depending on the action of elements in A on the vertex itself. So 0 plus 1 is 1, plus 2 is 2, plus 3 is 3. And if I do this for all the vertices, it's not difficult to see that this is what I have. OK, great. So we have built a graph starting from a group. Once we have fixed a set, this is called a Cayley graph, and we're going to use this construction for the next 40 minutes or something. OK, great. And now what I want to do is I want to define a code on the edges of this graph. So something that I can do, I want to exploit the fact that the graph is regular, and I want to use a code that is has the same length, delta, 3 in this case, as the vertex degree of each vertex in the graph. So in this case, I'm going to take the code that is the orthogonal to the repetition code. So basically, a code that has set as valid code words all the even bit strings. So let's start with the vertex 0. These 3 are the edges that are incident to it. And I'm going to try to write down a code word of the small seed code C. So I could select these 2 edges in red. Can you see the red? Yeah. And say that, OK, all good. Now, this choice of edges for the vertex 0 give me a valid code word for the code C. And now, if I want to build a code word of the quantum tunnel code, what I do is that I impose the same constraints on each and every vertex. So I will say that the valid bit strings for the quantum tunnel code that I indicate like this, tunnel GC, are all the bit string on the edges such that restricted to the local view, so to the edges incident to the vertex, they belong to the small code. So let's try to do this for fix this initial code word to a code word of the tunnel code. So I go to the vertex 1. You can see it only has one red edge incident to it. So I fix it, and I, for instance, color this one. Now it has even parity, so I'm good. I go to vertex number 2, is already even, so I'm safe. 3, no red edges, so it's even. And this tells me that this is a valid code word for the quantum tunnel code. And it's not difficult to see that this tunnel code particularly has dimension 3, and these 3 choice of edges actually give you a basis for the tunnel code. This is the complete set of code words, but for the code word 0. And yeah, that's it. So this is how you can build a code starting from a graph and a smaller code. And just to, get an idea of how it works, let's see about the dimension. So we have a set of vertices, the set of vertices in the graph, and we have a number of constraints that is the same as the original code for each vertex. So the total number of constraints that we're going to put in our tunnel code is upper bounded by the number of constraints of the classical code times the number of vertices. And with some easy calculation, we can see that provided that the rate of the classical code in input is not 1/2, we have a linear scaling of the dimension of the quantum tunnel codes with the number of edges. As for the distance, I will not go into the details of a proof, but I will only give you an idea. So let's take a graph like the one before, just a bit bigger. And what we have is that if I want a non-zero code word, what I do is that I pick a vertex, and then I impose that the edges incident to it are in the classical code. And what it tells me is that given only one vertex, I have at least a code word of weight the distance, beta delta, of the original code, which is good, you will say. However, what happens is that once you have enforced the constraint on one of the vertex, for each bit that is non-zero in that code word is going to be incident to at least another vertex, because this is what an edge is. And so each non-zero edge in this original code word will give rise to other non-zero edges. And each of these red vertices that are incident to such edges will give you at least a distance t code word for the classical code. So this tells us that if the graph is such that you don't have too many cancellation in between sets of vertices and the edge between them, this tells you that having one non-zero code word actually gives you a distance that scales linearly with the number of edges. And more formally, this tells you that if your graph G has good enough expansion properties, you can build in this way a code, a classical tunnel code that has distance scaling linearly with n. So now that we have seen how to build a classical tunnel code, let's try to build a quantum one. Okay. We want to build that quantum CSS code. So what we're trying to do is we try to have two classical code that are orthogonal. Let's see what we can do. So first, I will just give you a list of requirements that I want, and I'm going to build a graph, and you're going to accept this, and then we're going to see why we needed all those things. So we take a group, and instead of one set, we take two, because we want to define two codes, so that's quite common. Okay, we take the two subsets of the group to have the same size. Requirement number 2 tells you that you want the set to be self-inverse. So it means that if A belongs to the set A, also its inverse belongs to the same set. And third, we have this total non-conjugacy condition that say that the action of the set A on an element is different from the right action of an element B on the same element for each choice of A, B, and G. Okay, then we have two sets. We're going to build two Cayley graphs, as we have done before. So for instance, in the example before, I could have said that A is the set 1, 3, and B is the set 2. So instead of having a graph with all edges coloring the same way, I have something like that. It's just the same. So I take one vertex set that is in one-to-one correspondence with elements of the group G, and then I build the edges of the Cayley graph A and the Cayley graph B, just as I did before, but on the same set of vertices. And then I claim, this is a definition, that if the graph that I obtain, which is basically two Cayley graphs glued together, is bipartite, then I call this thing a left-right Cayley complex. Okay? And what is nice about the left-right Cayley complex is that we can define another object that are not vertices or edges on this thing, which are squares. So let's see. You have an element G, and then you know you're going to have an element of type AG, GB, and AGB. And by definition of your Cayley graphs A and B, how you build this thing, you know that you have these kind of edges. So you have A edges that connect G and AG, and similarly for downstairs, and so on. And you also have the B edges. So you are in a situation where for each G and choice of A and B in A and B, you have a square like that. So we say that on a left-right Cayley complex, we can consider the set of all squares. And in fact, it's not difficult to see that you fix G and GB, you can make A vary, and you're going to have like a set of squares that precisely size of big set A that have the same two vertices on this side, but changes in the other two. And so, we can, on such a graph, we know that we're going to have a bunch of these squares. So we can look at the set of all these squares. And now that we have built the squares, we can go back and have a look at what those conditions were actually giving us. So the first one, is not really necessary, but that A and B have the same size, but we decided to put it there just because it's easier. Then condition number 2 ensures that each vertex has exactly A delta edges of type A connected to it, and delta edges of type B connected to it. So this is important because it tells you that basically your graph has vertex degree that is delta square and is regular. And so condition number 2 ensures that. Condition number 3 ensures that the vertex on this diagonal are always different. And the fact that it's bipartite tells you that you don't have self-loops. So altogether, this means that each square in a left-right Cayley complex, so defined, will have exactly 4 vertices. They are all different, and yeah, and being bipartite, they have like the shape of a square, as you would imagine. So great, we have a graph that we have built starting from a group, and then we have added 2 sets of edges, and what we end up having is what is called a left-right Cayley complex, where we can define squares on it. And yeah, what I'm going to do is, instead of using before, I had a vertex. Yeah?
Yeah, sorry. I was just wondering this bipartite condition. How hard is that usually to satisfy? Is that sort of automatic, or do you have to try hard to get that?
So actually, in the original paper, instead of having this as a condition required by the graph, they take the double cover of the graph. So you take a graph G and you do the product with Z2, and then you do the edges in between things of different species. So for each graph, you can obtain something that is bipartite. So it's not for free, but you can, by paying double the number of vertices, you can find a bipartite graph. It's not for free. Okay, so before I was picking a vertex and then defining a code on the edges incident to it, and that was the edge space was my bit space. Now I'm gonna use, instead of the edges, the squares. So I'm gonna define 1 qubit for each square in the left-right Cayley complex. And I'm gonna impose constraint for each vertex in the set on the squares that are incident to it. And what is nice is that for the condition that we have said, we know that each vertex Z has exactly delta edges of type A and delta edges of type V. And therefore, since each square is uniquely identified by 2 vertices on its diagonal, we can see that the squares that are incident to 1 vertex in the graph are in 1-to-1 correspondence with element of A times B. So given G, I can uniquely identify all the squares that are incident to V, which means all the squares that have 1 vertex that is G as an element in the Cartesian product of set A and set B. Okay, so good so far. Now, I've said that I want to define 2 codes to build our CSS codes out of this construction, and then want the 2 codes to be orthogonal in the end. But what can we do? So let's, for a moment, as you can see from this guy here, I expect my graph to be a bit of a mess. So each vertex is going to have a set of squares that are disposed not surely on a plane. But for a second, we can just imagine to cut a tiny bit of our code, and by poor luck is the best possible configuration. So it's just vertices and squares on a plane lattice, and you're lucky. Let's see, it's bipartite, so that's by assumption. Otherwise, I will have thrown my graph away. So I have white and black vertices, and I'm going to use the white and black vertices to define the 2 kinds of stabilizers that I want. But let's see, I want the stabilizer to commute. So, I have to study what happens to the squares that are incident to a vertex of 1 type when I compare those with the vertex of the other type. So let's start with a white vertex. And, we have 2 cases. Either the 2 squares are very far, they don't have any edge in common, so they are disjoint, like in this example here. Or it's not difficult to see that whenever two squares, so two squares that are incident to one vertex actually overlap, so two vertices share the same square, actually this is equivalent as saying that the two vertices share an edge. So what I'm saying is that the only way for two squares of belonging to the neighborhood of a vertex of type 1 or type 2 is for them to be connected by an edge. So in this example is a kind of edge, but I could have had the black circle here, and it would have been a B kind of edge, but this is the only way two vertices can have non-zero overlap in the square space. And if what happens is that if two vertices share an edge, like in this situation, actually they share B different squares. And this is not difficult to say. As I said before, each square is uniquely identified by one element of A, one element of B, so I can just fix G and AG and make B varies. And I have size of B choices for this, and all these squares are going to be neighbors of both the blue vertex V0 and the red vertex V1. Okay, so what I've said so far is that we have the two vertices. I want to define a code on the squares, and I want to define two codes on this complex so that they commute. So first, I have already said the code is the classical code. The constraint that I want to impose are on the square neighbors of each vertex. And this is big delta square, so it's A times B, okay? And then I have that two vertices that have different color. If they overlap, they either overlap on an entire row of squares or on an entire column. So it's not that crazy to take as classical code on the neighbors of a vertex the tensor product of two classical codes. So the classical code CA tensor CB for two classical codes CA and CB has the right dimension, has the right length, is delta square. And if I pick CA orthogonal to CA transpose, then I find that, whenever I have some overlap between the bit string defined on the white vertices and the red vertices, then they overlap exactly on a row. But by definition and by construction, such row is made of orthogonal code words of the classical codes. So it's even. I'm safe. And likewise, if I look at the columns with B. So all of this to say is that once you have a left-right Cayley complex, you can use the bipartition assumption on the vertices. And then for each vertex, you're going to say that the quantum Tanner codes are Z stabilizer defined on the neighbors of a white vertex that respect the tensor product CA and CB, and likewise for the X code. So you take a Cayley graph, you take two, you look at the squares, and then we have defined a code on the squares of this graph. And it's not difficult to see, to have a lower bound for the dimension, and it's not difficult to see that it's easy to maintain a good dimension for a code built in that way. And as regards the distance, the proof is, let's say, similar to the proof that I've sketched you before for the classical code. And if your graph at the beginning has good enough expansion, then you can show that the distance is good as well. Okay, So now that we have seen more or less how to build a quantum tunnel code, let's see whether we can find some friendly example of those. I'm sure everyone is familiar with the rotated toric code. So what is interesting about it is that the toric code and the planar code, just the normal version, are hypergraph product codes. And the rotated version is not. However, it's very easy to see that the rotated toric code is actually a quantum tunnel code. So let's take a graph like that. So we have a grid of vertices of the integers mod 4 in this case. And we take the set A and B like this. So A edges are going to connect vertices like this with some boundary conditions. And B vertices are going to connect, B edges are going to connect vertices in the vertical direction. And, you know, first we can observe that in this way, delta is equal to. So if you look at the number of squares, which is the length of our code, is actually d square, which is what we wanted for the rotated toric code. And then let's go and impose the condition given by the two classical codes, just to double check that we do satisfy all the requirements that I wanted. So yeah, A is self-inverse, and it's easy to check the condition number 3, and also to see that the graph is bipartite. And so, you know, now we've defined the vertices. Each vertex is going to be associated to a stabilizer. So white one to Z1 and black one to X. Now, as each vertex only has 4 squares incident to it, I can uniquely identify a squares with its top left corner. So I can label qubits, which are squares in this world, like this. And, you know, with very little imagination, we can look at the dual lattice of this thing. And, you know, each white vertex is going to be at the center of a face. And each same for the X vertex. And it's not difficult to see that what we obtain, just by looking at the other picture, it was the same before, is what you would expect by the rotated toric code. So great. Yeah, I think it's nice to find a code everyone knows as an example of another code. However, what I've said before is, you know, the rotated toric code is not an hypergraph product code, but it's better because even if in asymptotic land it scales the same as the non-rotated version, it actually uses half of the qubits. And we have seen that it's quite easy to find the rotated toric code as an example of a quantum tunnel code. And what is, you know, maybe different is maybe a bit more involved, just a tiny bit, to find the non-rotated version of such a code as a quantum tunnel code. So let's try to do the same game, but we have changed the sets A and B. So this time, you're going to connect edges on the diagonal in this way and in this way. And what we can observe is that we have a tiny problem. So both elements, A and B, never change the parity of your vertex. What I mean is that if you start from a vertex ij, like 0, 0, and I plus j is even, then using A edges and B edges, you're going to just connect that vertex to vertices with the same parity. So again, even parity if you start with an even parity. And what this tells you is that we can divide the set of vertices in 2 sets, the even vertices and the odd one. And we see that what we have obtained is actually 2 disjoint graphs like that. So it looks like you cannot actually build a toric code starting from Z2 times Z2. Also, the number of squares was odd. But actually, we can just build the toric code focusing on one of the two graphs. So let's see what we can do. Now we have just one half of the graph we have started with. We can discard the other. And, you know, again, it's bipartite. I can draw a square for each square in this graph. And these are going to be into one-to-one correspondence with qubits. And it's not difficult, you know, to refine the usual toric code picture. I will just show you. You're going to do this. So basically what I'm saying is that, as you know, in the toric code, you have like these two kind of qubits that, if you draw in a grid, are just horizontal and vertical. And so in the quantum tunnel code pictures, you alternate between the squares, row-wise, and you find exactly what you were expecting. Yeah, so it's nice. We have been able to see two codes that we all know as an example of quantum tunnel codes. And what was interesting is that it was easy to build a code that had half the number of physical qubits to, you know, the toric code example. So this is what we would like to do. So the goal is just to find some example of codes that give you some improvement with respect to the hypergraph product code in terms of distance scaling and dimension. So we want to save qubits, basically. Now let's look at some conditions that are necessary for us to find such example of codes. This is what we are looking for. So let's start with these three conditions. So what is necessary for us in order to have all of these satisfied? So let's start with the definition. We say that two elements in a group are conjugate if they satisfy this relation. But most of you are familiar with this. And then it's easy to see that two sets satisfies the total non-conjugacy condition if and only if A and B are not conjugate. And this is, you know, just you can multiply by B minus 1 on the other side and then use the other lemma that says that if two elements are conjugate, then their inverse are conjugate as well. And, you know, we have already seen something like this before. So an easy corollary of these two things put together is that if you take an abelian group, as we have done with Z, the integers mod 2 before, and you just take two sets that do not overlap, then you actually satisfy the total non-conjugacy condition. And this is what we have used without saying it out loud when we had to build the toric code and its rotated version. But, and if we put these two things together, we can find that the TNC condition and self-inverse sets are equivalent at looking at the group G as a quotient with the conjugacy relation together with the inverse relation. So basically, I take the equivalence classes of G united with the inverse of G, and then take this quotient group and divide it in two sets. If I can divide this group G into two complementary sets that have empty overlap, then I can unravel again the two sets from the quotient group to the normal group, and I will find A and B that satisfies the TNC. So we're going to use this in a minute to create sets A and B. Okay, so we have an idea on what to do about the TNC condition. Now, the other ingredient that we needed, it was that we wanted the graph, in the end, to be bipartite. So we have a couple of observations we can do that we knew about already, which is, okay, if a graph is bipartite, then each cycle is even, and if it's bipartite, then, and with sets V0 and V1, and we have like a Cayley graph that starts from a group, then both sets that build the Cayley graph are in the partition that doesn't contain the identity. This is easy to be seen because, you know, in such a graph, all the edges multiply, left multiply or right multiply by A on B. So if you start from the identity, you can see that each element of A and B are going to be connected to the identity. And so if the graph is bipartite, they're going to be contained in the other half. And if we put these two observations together, then we can find some necessary condition that A and B and G must satisfy in order to obtain a bipartite graph. So we have that all elements in A and B needs to have an even order. That's easy to be seen because you can consider a path that starts from identity and always multiplies by A. This is going to be a valid path on your graph, and at some point you're going to reach the identity again, so it's a cycle, hence it's even, and therefore all elements in A and B needs to be even order. Then you can see that the two halves of the bipartition needs to have the same size, and this, you know, you can start basically for each element in one half, you can find an element in the other half. And you can see that by looking at the quotient in between G and the group created by an element, or just by, you know, you create a path like this one, you start from G, and then you do an alpha edge each time. And, you know, because the graph is bipartite, you will have that one other vertices is going to be in V0 and the other one in V1. And in this way, you can populate all of V0 and all of V1 like at the same time with a one-to-one correspondence, and you find they have the same size. These two things put together gives this bound, which is OK. So basically, if we build a graph starting from a group, A and B have the same size, we find that the cardinality of G needs to be at least as big as 4 times delta. And with another step, we can, you know, see that if we do a step back and we just start from a set C of generators of the group G, and we look at the Cayley graph, if this Cayley graph is bipartite, then for free we have that condition number 2 is satisfied. It's OK. So what I'm saying is that, OK, we have a bunch of necessary conditions for A and B, and then we have this thing. All of those things put together tells me one thing that I'm going to exploit to build small instances of codes. That is, I take a generating set of a group. I look at the Cayley graph, which is smaller to the graph of the left-right Cayley complex with the squares. It's easier to look at. If this is bipartite, then I can always find A and B that gives me a well-defined left-right Cayley complex. And this is what we have been using to look at small instances of codes. So we just take a generating set for a group G that has even order and is big enough. And then we check if the Cayley graph associated with the generating set is bipartite. And then we are able to return sets A and B to define the left-right Cayley complex. And yeah, so we have started to look at a small example. We wanted codes that were less than 500 qubits. And we have gone through like a bunch of parameters for n not too big. And these are maybe the only example of codes that we have found that are better in terms of dimension and distance scaling of the hypergraph product code. You can see in this quite ugly graph, here is the bound of square root of n for the dimension of the distance. And we have found something that is a tiny bit better. As I mentioned, 26, and k is 32. Stabilizer weight is still quite big, and probably, I think, a bit more engineer and thought on the choice of the group itself, and the base code has to be put, but is a first direction of smaller-ish standard codes. Thanks.
Hey, any questions? Yeah.
Thanks for a great talk. Just at the start with the classical Tanner codes, so you had like K and D scaling with like linearly in the degree of the graph delta.
Yeah.
I might have missed something, but doesn't that violate like the LVPC condition? Because then if your degree of your graph is like what scaled n?
No, you say scales linearly with the
Delta, the degree of the graph.
No, scales linearly with the number of edges. Sorry. So this is the trick. You're right that the bounds were written in terms of delta, but I just want the bounds. So the number of edges is the size of the group. So like G, whatever, so then times, so your code is defined on the edges. The number of edges is the number of vertex times the degree divided by 2. And so you find this. So you see that there is a relation where here there is size of V, which is bigger.
Oh, okay.
It is bigger than delta.
Okay.
And then is V times delta times something that is smaller than 1.
Right. So that's just a bound then in the like delta, rho delta, beta delta up top.
This is just as a good code works. Like you can have codes that have rho and beta are smaller than 1. So instead of, and you can have those things that goes linearly with n. That you can have.
Okay.
If you take a random code, like a random parity check matrix of low weight, you're going to obtain very likely something like this.
Oh, okay.
Yeah.
Thanks for the nice talk. I was wondering if you maybe are able to make any statements about like the code distance or the code properties relates to like the stabilizer weight. Like I saw on your table that like those codes that you found that were like good in your definition of good were like weight 12 and weight 16.
Of stabilizers?
Yeah.
So yeah, this is the stabilizer weight is upper bounded by delta square. That's for free because each stabilizer is defined on the neighborhood of a vertex, and the degree of the vertex is that one. I think that weight of the stabilizer could be improved by using a code that that basically has lower distance, because for the toric code, you started from a classical code that had distance 2, right?
Do you think you're restricting yourself by this like assumption of that like the size of A and B is equal?
But not really. It's just easier because not really. Maybe it was restricted because in the experiment in the table we used delta even. That can be just because it's easier to find the two sets that are self-inverse if delta is even. But that I think is not smart.
Okay.
But A and B equal size.
I might have missed this, but how are you searching over the local codes?
Small, tiny, there is a table of small, tiny codes, code where 4, 6, or 8 as length, and there are not so many classical codes. Yeah. So it's written like one is the extended numbing code, the other one is a cyclic code. Like good codes of that size are not that many in classical land. Okay.
Great. Thanks, Armanda, once again.
Thanks.